Hi folks, my name is Parvin Moorthy and my metric number is 10DKM22F2003. Today I would like to talk about the application of reverse engineering, which was an a practical task that was assigned for us on reverse engineering a existing product, which is a door latch. In our project, we focus on drawing and 3D printing a door latch, an element that is among the most commonly used in daily life for, as an as a as a security mechanism. In order to conduct a reverse engineering, we should understand what is a reverse engineering process and its devices for environmental sustainability. A reverse engineering is the process of deconstructing and analyzing existing products, system or component to understand their design, functionality and structure. This knowledge is then used to replicate, improve or extend the life of product. When applied to sustainability, reverse engineering can significantly reduce the environmental impact of manufacturing and consumption by promoting the reuse, repair, and recycling of materials. This helps to conserve resources, reduce waste, and minimize the need for new raw material. The key devices used in reverse engineering for sustainability is 3D scanners. 3D scanners 3D scanning technology plays a crucial role in reverse engineering by allowing engineers to capture the exact dimensions, geometry, and surface details of a physical object. These scanners can create highly accurate digital models of products or components without need for extensive trials and error. By digitizing the physical object, 3D scanners make it possible to replicate parts for repairs, replacement or enhancement without producing new component from scratch. This reduces material waste and lowers the environmental impact of the manufacturing. The common 3D scanners which are widely used in industries are laser scanners, such for an example, Faro laser scanner, or structured light scanners like Artec EVA, and handheld 3D scanners, Creaform HandyScan. For our project, we don't have these 3D scanning tools, so we used digital vernier caliper to get the dimensions of the door latch parts. CAD software also plays a major role in reverse engineering. CAD, which stands for Computer Aided Design software, is instrumental in reverse engineering by enabling the creation of precise digital models from 3D scans or existing designs. These softwares allows designers to modify and optimize the product design for improved efficiency, durability, or ease of repair, all while minimizing material waste. In the context of environmental sustainability, CAD software also helps to visualize and simulate the impact of design changes, ensuring that the redesign uses fewer materials and energy and is more resource efficient. For our practical task, we used Autodesk Inventor to redraw the existing product's part with the accurate dimension which we measured using digital vernier caliper, and later on we moved those models to Autodesk Fusion 360 to create the threading for screw of the latch and the main door latch. The environmental benefits of reverse engineering are minimizing the need for new raw materials, reducing landfill waste, and supporting the circular economy. That's all from me. I would like to pass it to Parvin Muthukumaran, which is my teammate, and thank you.
Greetings, my name is Parvin Muthukumaran and my metric card number is 10DKM22F2007, and now I would like to talk about 3D print parameter settings for material reduction. First of all, let's explore about the quality. The quality layer height is set default layer height. Layer height influences both the print time and surface quality of the finished part. By using default layer height, you can achieve a balance between print quality and material usage. For non-critical parts for the door latch, this setting can help maintain efficiency without compromising the integrity of the design. The next is infill. Infill reduce infill density. Reduce infill density to 20% for non-structural parts. Infill density determines the amount of time internal structure within the printed object. For parts of the door latch that doesn't bear significant loads, a 20% infill density is sufficient. This approach saves filament while ensuring that the part remains lightweight and sturdy enough for its purpose. Next is eco-friendly infill patterns. For the door latch project, we used honeycomb pattern, but also gyroid is also suitable. Patterns like honeycomb or gyroid not only provide structural integrity but also reduce material consumption due to their efficiency geometry. These patterns distribute force evenly, making them ideal for conserving materials in 3D print components such as a latch while maintaining functional durability. Now, material selection. Sustainable materials, example PLA. PLA stands for polylactic acid. It's a biodegradable plant-based filament often used for sustainable 3D print. Using PLA for our door latch project minimizes environmental impact while providing the necessary strength and durability for light duty applications. And now for the print speed. The print speed was set at optimized speed time for energy efficiency. Adjusting the print speed can reduce energy consumption and shorten production time. Increasing printing speed saves time, but if the speed is too high, it may compromise print quality, leading to potential reprints. For the door latch, an optimized balance between speed and quality ensures a smooth surface finish without sacrificing material efficiency. Support structures. Minimize supports by reorientating parts. In 3D printing, supports are structures that help maintain the shape of overhanging sections. By carefully positioning or orientating parts, it's possible to reduce or eliminate the need for supports, saving materials and reducing post-processing work. For the door latch project, reorientating parts minimizes unnecessary material usage. Breakaway supports are used in this project. They are easier to remove manually. It's a simple post-processing. This reduces waste and make the finish process cleaner, especially useful in complex geometrics are involved in the door latch design. The next is bed adhesive. Eco-friendly adhesive technique. To keep the print object stable on the print bed, eco-friendly adhesives methods such as printer's tape or low-impact materials can be used. These materials often offer a secure adhesive to build plate without excessive material use, help conserve resources, and also minimize rafts and berms. Rafts and berms provide extra materials around the base of the model to improve bed adhesive, but they consume more filament. By optimizing bed adhesives without additional rafts or berms, materials use is reduced, which is beneficial for both cost efficiency and sustainability in our door latch project. Now let's talk about environmentally preferable materials in 3D printing, which are PLA. PLA stands for polylactic acid, which is a renewable source. PLA is a biodegradable plastic derived from renewable resources, primarily cornstarch or sugarcane. This is contrast to conventional plastics that are produced from petroleum, a finite resource. By choosing PLA for your 3D print, you are using a material that comes from plants and replenishable, aligning with sustainable practices. Biodegradable properties. PLA can decompose under industrial composting conditions, meaning it can break down in controlled environments after its life cycle ends. Although it doesn't degrade as quick as in households compound bins, in fact that it is industrially consumable makes it a greener option than traditional plastic. For a project like door latch, which biodegradably might not directly impact function, PLA still offers a valuable environmental benefit in terms of end-of-life disposal, low emission during printing. Compared to some other 3D printing materials, PLA emits fewer violation organic compounds (VOCs) during printing, makes it a safer choice for indoor printing environments. This is particularly relevant if you are working in a small workshop or in an education center where indoor air quality is concerned. Next is PETG. PETG stands for polyethylene terephthalate glycol, which is a recyclable and durable. PETG is a thermoplastic that combines the durable and strength of ABS with the ease of printing associated with PLA. It is recyclable, makes it more environmentally friendly choice compared to non-recyclable materials. PETG can be reproduced and reused, which reduces the waste and aligns well with circular economical principle in the Dulwich project. Using PETG would provide the structural integrity needed for a functional component while offering recyclable at the end of its life. Lower environmental impact than ABS. ABS is a commonly used plastic in 3D printing, but it has higher environmental footprints due to its petroleum-based origin and more intensive production process. PETG, on the other hand, is considered a safer and more sustainable alternative for projects requiring robust mechanical properties. By opting for PETG, you are reducing the environmental impact of your project without compromising the durability need for a working door latch. High impact resistance and durability. PETG's resilience to physical stress makes it suitable for parts which will experience regular use or impacts, such as door latch. The material's toughness also means fewer breakage, reducing the need for reprints and thus conserving resources over time. Recycled filaments. Sourced for recycled plastic. Recycled filaments are produced by repurposing post-consumer plastics such as PET bottles or by recycling waste from other industrial processes. By choosing recyclable filament for our door latch project, we can help reduce plastic waste and realigns on virgin resources, making it more sustainable choice. This is particularly impactful in 3D printing, where material usage can be high and opting for recycled options can lead to significant resources savings. Sustainable for non-structural applications. While recycled filaments are sustainable, they are often better suited for non-structural parts due to variability in material quality. However, if the door latch design does not require extreme strength, recycled filament can be an eco-friendly option for components that won't face heavy loads. Using recycled filaments for less critical parts of the door latch can help reduce the environmental footprints on our project. Promotes circular economy. By integrating recycled filament in the 3D printing project process, you contribute to a circular economy where waste materials are reused rather than discarded. This reduces the demand for new plastic production, conserves resources, and lessens the environmental impact to manufacturing.
Hello, good morning, good evening, good afternoon, or good night, depending on when you are watching this video. Today I will discuss how 3D printers can address various community and stakeholder needs, providing valuable solutions and enhancing daily lives. Printing technology has the potential to revolutionize numerous aspects of our communities. One significant application is in education. Schools and universities can use 3D printers to create interactive teaching aids, enabling students to better understand complex concepts through tangible models. This hands-on approach can enhance learning experience and improve engagement. Another notable application is in the medical field. 3D printers can produce customized prosthetics and orthotics tailored to individual needs. This not only improves the quality of life for patients, but also reduces cost and production time compared to traditional methods. Additionally, 3D printing can be used to create anatomical models for surgical planning, providing doctors with precise tools to prepare for complex procedures. For business and industries, 3D printing offers significant advantages in prototyping and product development. Companies can quickly produce prototypes, test designs, and make necessary adjustments before committing to full-scale production. This iterative process saves time and resources, leading to more innovative and efficient product development. In construction, 3D printing can be used to build affordable housing solutions. By printing building components and assembling them on site, we can reduce construction costs and time, making housing more accessible to those in need. A prime example of 3D printing benefiting communities is the E-Enable project, where volunteers use 3D printers to create free custom prosthetic hands for children. This initiative demonstrates how technology can be harnessed to provide meaningful support to those who need it the most. In corporate world, companies like Boeing and General Electric have adopted 3D printing for creating lightweight and durable aircraft components. This not only improves performance but also reduces manufacturing costs and environmental impact. In summary, 3D printing technology holds immense potential to address various community and stakeholder needs, from enhancing education, healthcare, to driving innovation in industries. By embracing this technology, we can create a more sustainable, efficient, and inclusive future. Now I'll discuss some of the challenges we faced during our project and how we overcame them. First, let me briefly touch on the areas covered by my teammates. Parvin Moorthy discussed the initial design and considerations and selection of the appropriate materials for our 3D printer knowledge. And Parvin Uthukumaran focused on the CAD modeling process using Autodesk Inventor, highlighting the detailed steps to create accurate models. And also covered the actual 3D printing process, including the calibration of the printed and printing parameters we optimized to achieve the best results. One of the significant issues we encountered was replicating the 3D threading required for the doll edge using Autodesk Inventor. Despite our efforts, the initial attempts were unsuccessful, resulting in a model that didn't meet the necessary specifications. To address this, we switched to Autodesk Fusion, which provided more advanced tools for creating complex thread sections. After several iterations and adjustments, we successfully created the threaded section needed for the doll edge. This transition not only solved our problem but also enhanced our understanding to different CAD software capabilities. The comparison between the initial and improved models clearly shows the advancements we made. The final 3D printer model accurately reflected the design specification, demonstrating the effectiveness of using the right tools and technique for specific tasks. In addition to these points, my part of the project focused on the application of 3D printers to community and stakeholder needs. We explored how 3D printing technology can revolutionize education, healthcare, and industry by providing customized, efficient, and cost effective solutions. In conclusion, throughout this project, we gained valuable hands on experience in reverse engineering, 3D modeling, and sustainable manufacturing practices. These skills are highly relevant to modern mechanical engineering, where there is a growing demand for designers who are not only technically proficient but also mindful of their environmental impact. By successfully recreating the doll edge with precision, efficiency, and sustainability in mind, we have equipped ourselves with essential tools for the future of engineering design and manufacturing. This project has prepared us to tackle real world challenges and contribute positively to the industry. That's all for our project presentation. Thank you.